So first, let us now try to understand what motivated us for the SDN in the first place. One, where the control plane, where the networks were really difficult to manage, and we wanted them to be handled and made programmable in one aspect. The others were basically to break the ossification and to provide better means to innovate. That means to enable that any evolutions that happen which were typically slow to be made much faster. And this again requires the abstractions. In essence, we want to extract out the simplicity so that we are able to ensure that we can manage to build the right means to give the flexibility for what needs to be done versus what can be hidden as the key complex aspects underneath the abstraction layer. And in essence, we want to maintain and reason about the programs that manage and control the network. And how is the key aspect that was missing in the first part, or exactly saying what functionalities you want versus how they would want to be done. And here we want to look and understand what have the transitions that have been done, how they have been achieved, and how we want to take it forward. So to add on to what we just discussed, we have this typical match action pipelines with a parser and deparser, the packet processing capabilities in the data plane or the forwarding plane of the devices, which typically resembled the structure where the entire aspect of what the parser would do and what kind of headers that you are going to extract, what are the kinds of tables that you are going to deploy, support for what headers that we can match on were all decided by the ASIC vendor within the ASIC. And what this meant is if there was a switch that would say that it has support for VLAN, for L2 MAC, for L3, for ACL, each come with their own set of tables and the parser that were pre-baked to support these headers. And this meant that the ASIC APIs were closed, were not open for innovation, not open for experimentation either. And the way that these tables would be updated, configured, and the means to do that as a control plane was also a closed aspect. And on top of this, whatever the user had at a bare minimum was to work with the command line interpreters or the custom script interfaces which the OEMs, the vendors would provide and you would configure. For example, if we had a typical router, you are trying to interface and set up certain configurations, you log in onto the router, maybe SSH, maybe just TCP, depending on what kind of a router you have, and you would have custom commands like config interface, configure the IP addresses, set up the routing protocols, and likewise on switch in terms of what information. But you never had any control over how all of this would translate to setting up the actual data plane functionality. And this is where the SDN started to come and deossify or disentangle these rigidities by bringing in the right abstraction. With those custom ASICs or custom capabilities that were closed or proprietary aspects of dealing with the control or the data plane started to create a lot of troubles, especially as barriers in telecommunications and network infrastructures. And this is where an international research and industry communities known as OpenSig started in early 1995 with a concept of OpenSignaling and network programmability. In essence, to open up the aspect of how things can be brought for really making these networks to be programmed by the programmed or customized per need. And interestingly, there were many of the aspects that got pulled in terms of how to make these network control functions more open, extensible, and programmable. And also like we saw with the STN, the core aspect there was separation between the hardware and control softwares that you would want in terms of how the control software could dictate the hardware in terms of how to control the device. But now also as an aspect to see how this control over hardware in terms of what an hardware needs to do. And that's where the open programmable network interfaces were thought of. And there were a general switch management protocol as an IETF RFC that came out in the early 2000s in terms of what should be the key APIs with respect to which a switch kind of a device can be managed. And there were also initiatives from the IEEE, that IEEE P1520, which discussed the needs for standard software interfaces. That's basically for the programmability of the networks, specifically for service and signaling control. And when we speak about the telecommunications networks in the early era, the call setup, call teardown, handover, all of these signaling required a lot of management aspects and control that you wanted to establish as a programmable entity. And this is where this IETF P1520 started, where the objective was to enable the development of OpenSignaling, control and management applications, as well as like high-level multimedia services that wanted to be run on the networks. And the scope here was, although confined to the ATM switches and circuit switches or the IP routers, but these aspects, when we think, are also applicable to the traditional circuit switched or packet switched devices that we would want to work on, like the switches and routers. So the basic idea of how we can have a process of development as a standard for application programming interfaces for networks started to emerge with the early OpenSignaling works and these IEEE P1520 as a means. And what it really envisioned was to have the telecommunications network not as a bunch of hardware infrastructure, but think of it as a giant computer that can be fully programmed and controlled, which would help enable deliver the voice, data, video services globally the way we would want. That means it's more tangible to control and manage these devices. And the key intelligence here would vest with the networks in terms of how you would signal, how you would translate the algorithms to control how to manage the data, how to manage the forwarding plane of these devices. And the essence is carried forward in what we see as OpenFlow, and the aspect of looking in the core networking devices, which we saw earlier and discussed about the key changes. And now if we push back on what really did the OpenFlow really do in terms of working on these switching hardwares, it didn't change anything on the hardware pipeline. In terms of what contents you can parse, what contents you can match or take specific actions, OpenFlow had no control over how these things would be done. This would still be done as if it's a closed vendor, as a KPIs that would dictate it. But what it really opened up is the aspects above the control plane that could now be managed or externalized or centralized and be updated in a standardized fashion. Rather than having custom means to interact with specific devices, now it opened up a common vendor agnostic interface which would allow for easier network management and centralized control, and whatever you would write on top of this as a vendor agnostic interface could be reused and made interoperable across different vendors to make sure that things would work the same way. So that's where the code reuse and interoperability started to emerge with OpenFlow. And this pattern was, although applicable just at the interface of the control plane, but nothing underneath for the hardware. And what that meant is we still had these fixed function pipelines, and the capabilities for us would then still vest with fixed parser. Means if I have a OpenFlow, the OpenFlow headers, whatever we want to match and set up, they have to be supported by the underlying hardware. Only then would the OpenFlow variants work. And this is where, like, initially when the OpenFlow started, we saw that earlier we just had around 12 header fields, the standard L2, L3 and L4 headers that you would match and take specific actions. And there were action set was also pretty limited. In essence, we would only do like swap particular header, drop the packet or forward a packet on a particular port and so on. And this is what we refer to as the multiple match tables, which you could basically push. And aspect of how these tables and actions would correspond in each of these tables as we go along could be programmed through OpenFlow, saying what specific header match that you want and what specific actions that we could do was fixed. But I couldn't change in any way the configuration of a L2 table or add, let's say, a new layer 2.5 table. If it is not supported, we cannot change this. So this was fixed. But the entries that we want to populate in each of these tables is where the OpenFlow allowed to add the visibility. Otherwise, everything would have been done just by the device. And that's where OpenFlow started to bring more of visibility, more of control over what entries or what match entries and what action entries we would populate in each of these pipelines. But pipelines themselves, again, note that they were not something that could be changed with the earlier OpenFlow. So it didn't change the core network functionality, but it made sure that the control plane now became a bit more programmable. And going forward with SDN 2.0, what we would really want is not just that the control plane becomes programmable, but the control plane becomes open. In essence, we should have the control to dictate what should reside in this programmable parser entries and what should be the match that we would want, what kind of actions, if any, that we would want to add, support should also be there, and how many of these tables that we want, what kind of entries that we want to build should also be provided, needs to be programmed and controlled on these devices. That means end to end, when we look at what headers that we want to match and parse, that's the programmable parser, and what kind of actions that we want to take, how do we want to pipeline and process any of the packets, we want full control over that, and that also needs to be a programmable match action pipeline. And once we do take specific actions, how we want to deparse or basically assemble back the packet and emit the packet out on a given port, the control should also be there on all of these entities. And this was exactly the vision of programmable switches. Here, basically what this meant is to say that we can change, mix and match which tables would look for what headers. We could have table 1 look up for layer 2, table 3 look up for the ACL, table 4 look up for MPLS, or any of the custom headers that we want to bring in. We can bring in and say I add that particular functionality on any of the tables. So we can dictate the number of tables or match actions that we would want to perform, how many of those that we want to perform. All of this flexibility needs to be provided. In essence, we are making the control plane now completely open, and also the ASIC APIs that would then match for making this aspect on the given ASIC somewhat a licensed or a closed, even though closed or a licensed fashion, we could still have target specific applications to translate this open control plane activities into this ASICs through the either target specific or somewhat licensed APIs through which we could build this functionality. And to enable this is now the question of what exactly we need. And we can think of like the key changing interfaces that we would want to bring are either like a C or a Python APIs that could auto-generate and build what we call as program the open control plane to ensure that we can meet. And this is where the P4 runtime, which was the effort led by Google early on and now being a consortium in its own and trying to provide the means to facilitate the interfaces for really dictating all these elements. And in essence, what we have now made is the control plane to be fully open and ensure that the customizations can be pulled in just as a user writes a program, executes them on the hardware. You would have the programs that are written by the user and execute them on a hardware. And for this, the hardwares also need to ensure that they have the support for the P4 runtime support to be provided, and they are able to do both target agnostic and target specific actions within a given hardware. And what this would bring is provide us the core flexibility for doing how to do the packet forwarding and what kind of packet forwarding we want to do. And the reasons are quite simple. Like if I want to modify the set of packet fields, especially when we thought of network virtualization and overlay networks, it called for a lot of tunneling formats. Like we have NVGRE, VXLAN, and so many ETH in ETH, IP in IP, and so on, and STP. All of these need to be supported. That means we cannot be confined to just one set of specific headers. We may have to look in recursively into the packets, VLAN, all of these. And this required us to have the need for flexible packet forwarding. We couldn't have these tunneling supports unless the ASICs support. And we want to build custom tunnels. That means we want to have the ASICs support them readily. And also the support for new flags in terms of what way we would want to support, like RECN bits. If we were to enable them and try it out, we should be able to do like DSCP bits or TOS bits that we want to verify, change, adapt for any of the use cases. We should be able to do that. And in fact, the other way of looking at it is also if we disable specific fields and I want to bypass a custom layer 4 and jump directly to layer 7, maybe we don't want any TCP or UDP being there, just try out some other custom layer 7 on top of layer 3. Would that be possible? That meant that we should need the means to disable the existing fields, bypass them, and still support forwarding the packets or processing on the packets with customized headers. And this is where the need for flexible packet forwarding arrived, and catering towards this were all the changes where we needed the aspects to be looked in a different perspective. And also, like when we build specific tables, like think of I am deploying a router that is at the core versus a router that is within a campus or an enterprise network, where especially when we look at the campus or enterprise networks, they are really more particular about the access controls in terms of which flows should be permitted, which flows should be denied, and what are the actions that need to be taken in each of these access control modes. But when we look at the networking core networks, they are really heavy on just forwarding based on the IPv4 or IPv6 headers. So if we had such match action tables given by one vendor where you had the tables given for ACL, tables given for IPv4, you may not be utilizing the resources equally either. Because core networks, you'll be not using ACL tables. That means you are wasting those resources, wherein in fact we could have used the same for much more rules at the IPv4. And likewise at the enterprise, we may not be using the layer 2 or layer 4 or layer 4 or layer 3 of the types, but looking primarily at the ACL rules. And if we want to increase the ACL rules at the cost of other headers, other tables, we may not be able to do. That means again we are wasting the table space that otherwise the hardware would have been allocating for ACLs. And this is where again we needed more flexibility in defining not just the kinds of tables, but also define the size of the tables in terms of what should be the width that they should have, what should be the depth in terms of how many rules they can accommodate, and how many number of bits they should match in terms of the width, and so on. So the characteristics of actually having a full control over the tables was also the need to ensure that the resources would be used appropriately. And again, if we reflect back and see why OpenFlow was not sufficient in these aspects, we can see that OpenFlow started with just the simple match action, wherein the predefined set of fields that would be supported by the ASIC were only to be programmed. And initially it all started with a single rule table, wherein what we call as the single match action tables or SMTs, where all the sets of rules would be just baked in a single field in the early OpenFlow 0.9 and 1.0. And then it evolved into multiple match action tables. But OpenFlow was not able to facilitate or support any encapsulation formats or different versions of protocols which we could readily build, like any of the layer 4 newer protocols. But if the action tables were not supported in the OpenFlow headers, it would not be able to support or configure such rules. And also any additional measurement related headers, if we had to add, like if you want to track or probe certain aspects of a particular kind of a packet, it would be difficult unless it was supported in the OpenFlow rules in terms of what could be matched. And these requirements in fact led to various versions of OpenFlow being evolved in terms of OpenFlow 1.0, which was just having around 12 fields, to OpenFlow 1.5, which came up to support around 44 such match tables. And having these different matches, that meant you need multiple kinds of tables to be supported within the hardware. So for each stage, you need different kinds of tables. So all of these led to saying, okay, just the OpenFlow approach of trying to match or on a specific field and take certain actions would not be feasible unless we really controlled the way we would want to configure the tables themselves. And this is where, again, this protocol independent switch architecture came to say we now not only control just the programmable parser match action pipeline, but we would want to specify for each match action stage what should be the table width, table depth, and for each of these processing, how many number of tables that we would want to support. And these basic features were the call in for what we call as the reconfigurable match action table design, wherein the first of the component is the programmable packet parser, where the parser block could be configured and updated with respect to what you want to see as what headers you would want to extract, and the pipeline structure in terms of the match actions that we would want to do. We could have multiple of these pipeline stages, and each of these stages could be done one after the other at a very high clock rate so that we are able to meet the line rate packet processing. And the match action logic in each of these tables could be completely distinct. And whenever we are trying to build these match action logics, we would also want to have support for specific counters or statistics for certain kinds of a match in terms of how many layer 2 packets were with this particular destination MAC, or how many of the packets for a particular layer 3 address on particular port. All of these counters, etc., could be managed within the switch in terms of even how many packet losses were observed for each of the ports, what was the overflow, or what is the port utilization. All of these counters could be built up. And what this also meant is we would also want to keep the state on the switch in somewhere a stage local memory. For each stage, when you process, you change, you maintain information and then carry it forward. And these are exactly the aspects that we're looking for in trying to define what we call as a reconfigurable match table. And with this, what we would really end up seeing is to have a flexible parsing and be able to match on non-standard fields. That means we would be able to program the parser to match on the different kinds of fields which may be custom built and not necessarily standardized. And this would also make a faster and easier network evolution, because now we have the ability to test out the newer protocols on the hardware in a much more quicker fashion, because now we can write parsers in minutes and then run them on devices much more quickly. And likewise, when we see, this would really break what we saw earlier as a traditional protocol design that would take several years. And now we are no more inclined to saying there is a need for hardware upgrade to facilitate support for certain protocols. It's just a software upgrade that would enable the new feature to be baked into the device and make it ready to operate. And this also is a key for the breaking down on the investment or lowering the investments that you would have on the hardware, where you are trying to reuse the same hardware with any of the software updates that we can make as long as the resource constraints are met. And through this, the hardware would go beyond on providing the data path processing primitives, that is, whatever are the existing primitives, and we may want to build newer primitives which may be a combination of the existing ones to build or bake in the new functionalities. And to do this, what we would need is a domain-specific language like a P4 that we will look into, so that the resources are made accessible and programmable through a construct of a high-level programming language or a domain-specific language for the switches. And it is just as a compiler abstracts the high-level language and the target-specific aspects, we want the P4 to abstract out the target-specific aspects and present the rich interfaces for what a programming language would cater and meet the target-specific requirements as necessary. And overall, this is how the researchers proposed an ASIC-level solution for new and existing problems and readily realize it, which would enable them to realize it very readily in the production hardware. And what this would also call for in addition is the need for transactional memory and stateful ALUs, wherein we want to persist certain data as we process the packets, as we parse the packets, and as we configure the operations on these packets. So the stateful operations that we would want to do across multiple packets, if we want to tag and tailor the counter, or you want to do the segmentation, we want to do the fragmentation, all of these would require you to maintain specific state across processing of multiple packets. And that's where the need for a transactional memory would be useful. And then you would want the ALU, which would do basically the set of simple computations. It could be add, subtract, or an approximations of multiply or divide, wherein just an integer multiply or integer divide would be able to work out, or you want to compute certain averages, or like what we use the EWMA kind of aspect, how you can do the approximate of these computations within the data plane of the hardware. And also what this would enable is also provide what we call as a telemetry information in terms of how much of the time the queues were occupied for a given port, or what is the depth in which the queue or the queue occupancy is being seen, what's the average queue occupancy, what is the time spent for packets in each of the queue. All of these informations could be extracted, and even we could present very high resolution timestamping within the devices to say when exactly the packets arrived, at what time the packets went, on a nanosecond precision. And this way we could basically enhance the functionalities that otherwise the data plane primitives were having but not exposed, but now being exposed for the programmer to utilize them and build specific characteristics. And in fact, when we want to monitor the traffic and want to see what kind of activities are going, we may want to have packet cloning and replication capabilities so that we can mirror the traffic and see what's going on at a different kinds of analytics or monitoring devices. And we could also do conditional multiclasts so that the packets can be sent out on different ports. So all of this calls for what we see as better abstractions that can be built in terms of abstractions for what way the parsers need to be built, what are the headers that we want to augment, and what are the kinds of tables and control flow that we would want to dictate on each of these devices. Wherein in this example, we can see that if I have to build a parser, the parser would start with a layer 2, a typical Ethernet, and then from the ether type, you would want to extract what would be the next higher layer that you would want to look for, be it a VLAN, be it IPv4, MPLS, or if nothing matches, you want to just fall on with the default ingress approach, wherein any packet that has come, you just treat it with respect to the port. And maybe this is a packet that is some informative thing that is meant only for a switch, you would want to handle it locally. So all of these functionalities could be baked in, and ability to add custom headers thereof. Like if I say that a switch by default doesn't have any notion of what is a layer 2, layer 3, layer 4 header, but programmer dictates the switch to consider Ethernet as a layer 2, IPv4 as a layer 3, MPLS on top of Ethernet as a alternative layer 3 to look for and then process. The intelligence of what to parse and the intelligence of what tables or what actions to take is all being baked into these devices from the program, rather than the device coming up with its own intelligence that we want to tamper. And with this flexibility, what we would want as abstractions to be provided for the user to build a device with the P4 constraints. And these better abstractions would then readily enable the developers to write programmings for the networking. And we can now reasonably think of how we write a program on the general CPUs to be the same way as writing what we want to do with each packet and express that in a programmatic fashion. And to do this, the programmer doesn't have to address or cater to the specifics of what header fields or what specific tables, when these can be matched out on the target specific aspects. But a programmer should be able to dictate what headers that he would want to look for and what way that if there is a match on the header, what actions to take. So the intent aspect would come from the a user or a programmer, and how of the things to be realized on a particular ASIC be handled by the target specific component in a compiler. And this is exactly what we have been very familiar with the von Neumann architecture, where we write the programs and let the CPU execute them for us. And the same way, now we write the programs and let the hardware execute it for us. And this would also enable us over time to build better compilers that can translate these abstractions to actual hardware in a much more efficient, performance-oriented fashion. And algorithms also can be tweaked to allocate the right resources so that they are optimized on memory, optimized on processing, and these can be done automatically behind the scenes as the compilers evolve. And this would also present a nice case to say that we implement the code once, implement it well, but execute it on different hardwares and different types much more readily, just as what we would do with very high-level languages, the programs that we write in high-level language. And further, this would also enable us to build what we can see as having the verifications of the code that we would build to establish the behaviors within the network. Now think of this network program as a contract between the control and data plane, and we want to verify whether this contract had been done correctly or not. So we could even bake in the programs to do this kind of verifications. And this would enable us to even rationalize and see what could be the problems and how they can be tackled in a programmatic fashion. And this brings us closer to saying, okay, we are now interacting not with a network as a hardware, but network as a software that is being programmed and able to provide the agility of how things can be brought into the networks. And this would readily help minimize the complexity for many of the network operators, for any of the features that they would want to bring in, any of the bugs that they would have to track or debug. All of this can now become much more easier to handle. And also it would be open for innovation in terms of bringing in the new ideas as softwares and deploy them on the hardwares, rather than waiting for the switch vendors to build the new things. And this is how the innovations in networking can sprawl. And one of the other important aspects that really has come up is the telemetry, like we did mention briefly about it. And what it really enables is to debug precisely if my packet is lost, why it was lost. If my packet is experiencing delay, for what reasons, for what aspects are really accounting to this delay, why is there an anomaly with respect to certain behaviors of certain switches or routers, which links are creating trouble. All of this, if we would want to monitor on a per packet basis, if we have the visibility at how each packet is processed within and we are able to control what each packet goes through, then we can definitely achieve this kind of a monitoring and extract this information much more readily. So measuring the networks more effectively and collecting lots of data that we can build and process becomes much more easier. And this is where again certain aspects also started. We will look into this in a bit about what we call as in-band network telemetry, wherein if we want the networks to program and if we want networks to dictate when things go wrong or when things are right, in terms of events that can be propagated, in terms of messages that can be communicated, what is the means to do it, how we can achieve it. All of this can be realized through this when we have the control over the forwarding plane in full. And that's what the P4 tries to achieve. And through INT, we would also be able to achieve a fine-grained network telemetry. So if we think of all of this, what we have now said is we are trying to go towards a programmable switching chip and get rid of the custom ASICs that otherwise would come with the closed APIs, but rather make those programmable. But then we also have to think of what is the cost, performance, and power overheads that these programmable switching chips bring. And like I said, this evolution happened over the last few years, to say almost around 10 years. And now we are having these devices like P4 programmable Tofino, which is basically a barefoot Tofino device now acquired by Intel. Here we can observe that the forwarding rates that we are able to achieve with these P4 programmable Tofino devices are on par, and in fact better, like 5.1 billion packets per second on a programmable switching chip, as opposed to the fixed function switching chip that's providing around 4.2 billion packets per second. So the forwarding rates, you can see, are likewise comparable and in fact better with this programmable chips. And when we see from the power that these devices take, again we can see that the typical system power drawn, 4.2 watt per port, seems to be much more reasonable than the fixed function switching chips with 5.3 watt per port. That means we are good on power, we are good on the performance. And likewise, if we consider the latency of packet processing that is happening, you can see that they are both around 100-400 nanoseconds. That means the performance metrics and the power metrics are all on par with the fixed function switches that we otherwise see. And in fact, now because these are programmable, we are able to support many more of the functionalities than just providing the switching capabilities. Like we can account for NAT within the programmable switch with roughly around 100k rules that we could support for NAT, and likewise access control lists that could be configured for again the same. So we could use either of like the NAT rules or ACL rules within an enterprise network, or you'd want to use the same for just supporting the P4 tables within the core networks. That customization allows to use the same device in the way that the real utility is for a given device. And analytics, again, like if you look as a key aspect, we can do line rate per flow statistics as opposed to just having a SFlow, which is basically sampling method for 1 out of n packets that you would want to capture and try to predict the behavior. So you would be able to do better fine-grained monitoring as well with these kind of devices. And this has happened primarily because of a lot of evolutions that happened over the recent past. And in every other aspect, if you consider the number of ports that you could support, 25 gig, 10 gig ports, the numbers or the CPUs that you would use or the power supply that you would plug, all of these aspects remain the same. So the number of 100 gig ports, around 64 in both the cases. And so there is nothing as what we would consider that the programmable switches would have degradations in performance or in terms of power are no more true. And this is where the case for many of these programmable switches have already made the inroads into many of the data centers and enterprise networks. In fact, Microsoft Azure have more or less replaced. They came up with the smart NICs that they deployed in early 2015s, and now they are moving towards these programmable switches. Nonetheless, there are specific limitations when it comes to the data plane programmability that we also need to keep in mind. One is there are specific high-level constraints in terms of if the device needs to meet the line rate processing, like when we speak of line rate, I mentioned in the last lecture, like if it's a 10 gig NIC with the very small packets of 64 bytes, you would end up with having to support almost roughly 14.88 or 15 million packets per second. And as we scale from 10 gigs to 100 gigs, you're speaking about like roughly 150 million packet per second rate, or at least around 50 million packets per second when we consider around roughly 200 or 256 byte packets, and likewise. So this means whatever the match actions, whatever the parsing that we want to build should ensure that it ends, and there should not be any loop construct which would make the things run in an infinite fashion. So support for loop constructs is currently not supported. And we also know that floating point computations are intensive. And hence, it could be possible that we can add a floating point coprocessor and do the computations. But in fact, it is much more easier to do if we can do approximate computations or integer computations within the switch, so that we are both time sensitive and be able to do with less of power. So the floating point of computations are currently not supported in the P4 part. And also, if there is an entry that is going to be read and updated, the way we access the memory can add up to the latency, especially if you are trying to write, update, and read the changes. Then you may end up having a lot of cycle stalls for accessing those memory. Hence, the accesses right now are basically single ported per stage SRAM memory, where we could add multiple ports, but that also comes with a cost and overheads. And hence, by keeping it simple, having a single memory entry for read and update in one packet pass. So that means that you would want to read, update in each of these stages as you go, rather than having to do read, write, updates in a simultaneous fashion, which could be addressed in the later stages. And these aspects essentially in a nutshell define the overall aspects of the programmable forwarding data planes. And to understand them in a lot more detail, we would have to look at these two papers, that's Forwarding Metamorphosis, that's Fast Programmable Match Action Processing in Hardware for STN, which was exactly the RMT paper. And follow-up is the P4 Programming Protocol Independent Packet Processors, which was a SIGCOMM CCR paper in July 2014 that would lay the foundations for better understanding of the programmable forwarding planes.